How do I know this? Because I need a T0 to integrate. I know that W0, I know T0. When I integrate, I know T0. I know that velocity at that point. If I don't, if my integration has a bias, right? The initial condition is not correct. For example, I integrate cosine omega t. Then I have omega sine omega t. Then T0 to t. I have to know T0, right? If I don't know T0, then this integration won't be good. Alright, so how can I solve this problem? Fast. The T0 problem. So either one, you don't get lunch for free. There's no free lunch. You do differentiation, you got a problem. Because you can be very noisy. You do integration, you got a problem because you got some bias. T0. Because you don't know. If you don't know that, then you have a problem. So, but many cases, what you can do is, we call calibrate. We call calibration. In other words, I have to have some way to measure my initial T0 velocity. So in space applications, then most likely they will use two kind of sensors. One sensor is just for calibration. One sensor is for integrations. So you can have a gyro, or you can have an Excel and integrate to get some information. And then I can have a star tracker to calibrate. Right? So this is the PID. Now, the PID, we know the PID, right? P is a position, I is the integrate, and D is a differentiate. Right? That's what we call PID controller, if you know the PID controller. So, when you try to integrate or you try to differentiate, you have to be very careful about those missing things. Like differentiate, you have to worry about the noise problem. Integration, you have to worry about this initial condition problem. Correct? The integration has advantages because it's 1 divided omega, and this omega is very small. Then if large omega means it's smooth your signal, because the integrations, when this has a noise, when this W double dot has noise, the noise, then you integrate that because it divided by omega. If your noise is high frequencies, then it divided by omega means smaller frequency. The noise will become smaller. The higher frequency you got in your noises means after integrate, your noise level will be reduced. So integration has advantages, but its disadvantages is how can you get the T0? Because you have to integrate from T0 to T. You have to worry about those. When you design a controller, you can simply say, oh yeah, I can integrate that signal to become the velocity. Yes, true. But you gotta worry about this. You can differentiate the signal and you got a velocity. Yes, that's true. You gotta worry about the noise because you amplify noise when you differentiate the signal. You reduce noise when you integrate the signal. That's true too, right? So that's what happens for these 3 different sensors. All right, let us look at this typical TMD problem here. Now, here, the WC, ZLC here, MC, this with C means I add a controller. For this case means I have displacement feedback and also have a velocity feedback. If I have a displacement feedback and a velocity feedback, and this is like a TMD, and it works like a TMD. Even you are doing a feedback. This is feedback. If I have ZC, that's from my velocity feedback. I have a KC from my displacement feedback. Assume I have two different sensors. One is displacement sensor. One is velocity sensors. And I give them feedback. If I do that, then for this case, this is like TMD, right? So the KC, ZLC, MC is a TMD. But this is active TMD. Right? So this is not like a passive TMD, and this requires power. We need a computer power, we need a sensor power, we need actuator power. So we also need a sensor, we need an actuator. However, this KC, MC, ZLC here, this is not physically exist. We don't have physical spring, KC, we don't have physical ZLC. This is all virtual. This is all by gain. KC is my gain. ZLC is my gain. Right? Okay. So if I do this, if I happen to have a displacement feedback, I have the velocity feedback, then I can design a feedback system which is mimic to a TMD. And if you do that, if your feedback KC, ZLC is all positive, then you will see that they are a stable system. Doesn't matter how much KC you got, doesn't matter how much ZLC you get, it's a stable system. As long as KC and ZLC are positive, this system is stable. Agree? Right? That's what I mean, the model independent. The KC, ZLC, as long as they are positive, doesn't matter what kind of K you got, what kind of system K you got, this system is stable. However, performance-wise is different. Performance-wise, we'll look at performance later. What kind of performance you are going to get? Then, depending on how much KC you put and how much ZLC you put. So that is the 2-degree freedom screen system, and this is similar to your homework 3. Your homework 3 is the TMD, but you can implement your TMD using the feedback system like this. The advantage of the active TMD, well, I call it AVA, that means you can change your KC, you can change your ZLC. If you don't satisfy, you are not satisfied with your performance, then you can change the KC, ZLC. As long as your changing is all in positive sign, then you don't worry about stability problem, because it's always stable. But if you change the sign, KC changes to become minus sign, and ZLC is minus sign, it happens like that way, by human error, then you will have a big problem, because the system becomes unstable. So feedback system has its disadvantages. If you have a human error, happen to change the sign, then you got a problem. All right. So that is the TMD system. The energy dissipations will be proved in here for the metric system. Our time is up. Stay now. Do you have any questions? I'm talking about very basic here today. to change from the passive TMD become active TMD. Okay, so this is like this. Today, I'm talking about very simple idea. How can we go from passive TMD? How can we go from this passive TMD? I call passive. Passive means no power required. Then it becomes, this is active TMD. And this is no power. This require power. And this we call ABA. It's an active virtual absorber. And that's the, next week I will try to complete the ABA. And the concept-wise, you will see that there's a lot of concept going on, and also there's real experiment here. I'll show you for that. Any questions about it? Okay, now let's end our class today.